standard 11.2, which reads, I can use the Lagrangian formalism to derive angle as a function of time for a double pendulum. So the Lagrangian is kinetic minus potential. So if you look at our double pendulum, we have the first pendulum with length 1, angle phi1, and mass m1, which has the second pendulum with length L2, angle phi2, mass m2 attached to it. We'll be measuring any vertical height as a function of from the origin being the top of the first pendulum. So for potential, you have mgy, and for the first one it's mgl1 minus mgl1 cosine phi. So anytime it's not hanging straight down, it will have less potential. And similarly for the second, it'll be the sum of what's happening with the first one and then what's happening with the second pendulum. And then reducing the potential to be a function of phi1 and phi2, you get m1 plus m2 gl1 times 1 minus cosine phi1 plus m2 gl2 times 1 minus cosine phi2. So now kinetic energy. For the first one, it's just going to be 1/2 m1 l1 squared times phi1 dot squared. But for the second one, I'm going to break it up into the x and y coordinates to give its potential. So this is the horizontal and vertical velocity. So breaking that up and using what I already have for position in the x and y, just taking their derivatives and then adding them, you get this equation for kinetic energy of the second. And then when you add them together, this is what you get for the total kinetic energy. So now we have the Lagrangian as T minus U. But when you're looking at both equations, both are nonlinear because they vary both with these cosine terms. The cosines are nonlinear terms, so you can't just solve it like we normally would. So what we do is we assume that phi1 and phi2, which goes to phi1 dot and phi2 dot, are super small. So if we're looking at the kinetic energy, the term that is influence is this phi1 dot, phi2 dot, because when you have two very small numbers, because we assumed that they were small, and then multiplied them by the cosine phi1, phi2 term, you can assume that that goes to 1. So this is what the kinetic energy is reduced to. Now for the potential energy, you have to do the series expansion of phi at 0, because we assume that cosine of phi is essentially cosine of 0. So when you do the series expansion, you get 1 minus phi squared over 2 plus phi to the 4th over 24, and then going on and on. But you can assume that any term with a phi more than squared is negligible, so you can just reduce it to 1 minus phi squared over 2. So substituting that into the potential for cosine of phi, you'll just get phi squared over 2. So that's how the potential is reduced. So when we are taking Lagrangian and subtracting them, this is what you get for the entire Lagrangian. And first you have to take the time derivative of the Lagrangian derivative with respect to phi1 dot and set it equal to the dl d phi1. So taking the first term with taking the Lagrangian and reducing, this is what you get for the first. And then doing the same thing for your phi2 terms, you get this. And so when you're putting into the matrix form of m phi double dot equals minus k phi, you get m is this term of m1 plus m2 times L1 squared, and then m2 L1 L2, and then m2 L1 L2 and m2 L2 squared. And then for k you get m1 plus m2 times GL1, 0, 0, m2 GL2. And then, so from there, we have to find phi of t, and it will be the real part of the z of t function, where the z of t is the solution to the differential equation, and with the general form of a1, a2, e to the I omega t. And so the general form steps that will follow is substituting z of t into the mx double prime minus kx equation, and then using k minus omega squared m times a equals 0 to solve, and the determinant to find the normal frequencies. So if we assume that there are equal length and equal masses, we know that the natural frequency of one pendulum is radical g over L. So solving for g, you get g is L omega naught squared. So to reduce the number of terms and simplify our equations, you get that m is now ml squared times the matrix 2, 1, 1, 1, and k is now ml squared times 2 omega naught squared, 0, 0, omega naught squared. So substituting into k minus omega squared m, you get this initially, which it kind of got cut off on the screen, but then it reduces to this ml squared times 2 times omega naught squared minus omega squared minus omega squared, omega naught squared minus omega squared. Now to find normal frequencies, you set the derivative of that what we just solved, or the determinant of what we just solved equal to 0. So the determinant is just a subtraction of the crosses, and you get two natural frequencies, or two normal frequencies. Omega 1 is 2 minus radical 2 omega naught squares, and omega 2 squared is 2 plus radical 2 times omega naught squared. And now to find the motion of the pendulum in each normal mode, you set the k minus omega naught squared m times your a constant equal to 0. So in case 1, you were substituting in omega 1 and reducing to get this equation, and now we're setting that equal to 0 and multiplying by a, and you get this equation. And the only way it can be satisfied is if a2 is radical to a1. So if you let a1 be big A times e to the minus delta 1, you get phi of t is reduced to a1 times the matrix 1 over radical 2 cosine omega 1t minus delta 1. So you can see in the first mode the pendulums oscillate in phase with the amplitude of the lower being 2 times the amplitude of the upper. And now for the second mode you follow the same process, but now we're substituting in our omega 2, and you get the difference in this case is now a2 is minus radical 2 a1, and so your phi of t is a2 1 of matrix of 1 and negative radical 2 cosine omega 2t minus delta 2. So in the second mode the pendulums oscillate out of phase, completely out of phase, and phi2 is now radical to V1 as well. So then the general solution is just the linear combination of the first and second normal modes.